Okay. Let's talk about Hückel theory. So Hückel theory is a way we can apply all the things that we learned about for the secular equations, some stuff with quantum mechanics, and the variational principle. What type of systems are we going to look at with Hückel theory? There's one very specific case. Yep, planar pi systems. Okay, and what is going to be our basis set selection? Yep. Yep, we're going to pick two p orbitals. So one per carbon atom. Right now, they're atomic orbitals per carbon atom. Okay. We set a couple of things equal and define some terminology. We had alpha and we had beta. I didn't really describe what those things mean yet, but we will in a little bit. How was alpha? What's the shorthand for alpha? It was H what? IJ. Yep, IJ. And then beta, did I say what beta was yet? Okay, but I didn't indicate a symbol. So this is HII, this is HIJ. Did we talk about that yet or no? No? Okay. Then we have Sij, which was equal to a delta function. So what does the delta function mean again? Alpha is HII, beta is HIJ. I must have. Yeah, it was meant to be an II, not an IJ. We could leave it as IJ. We'll get there in a minute. We'll see in a minute. Yeah, it was meant to be HII. So wrong last lecture, my bad. That delta, what does that delta mean? If it's true, it's one. Don't say true or exists. Yes. If they're the same function, it's 1. If they're not, 0. Okay. So we have some other rules that we talked about last time, and we're going to apply those to a system. We're going to look at a chemical system. And after we learn about this chemical system, we're going to start applying this to solids later on down the line, starting with a one-dimensional hydrogen chain and moving to, I don't know, p orbitals and d orbitals in a chain. Okay, so let's use this to explain the reactivity of an allele. Okay. Katie, you may not have ever seen, that is not an I, that's a colon, what an allele is. That's an allele. What's another way we could represent this thing with a Lewis structure? Yeah. And dotted lines. Okay. Now this system's delocalized, meaning the electron density is smeared throughout the molecule, correct? So knowing that, if you were to guess without any prior knowledge, if I wanted to react to this thing, it looks like carbon number 1, carbon number 2, and carbon number 3 should all kind of behave the same, right? It's delocalized, so it should react at any point in equal probability. Those who've taken organic, what do you know about this? So, only reacts on the ends. It's incredibly frustrating. Now, you're taught to just sort of memorize that and know that. But what we're going to do is we're going to take a mathematical approach to explain this. I personally hated the wizardry of organic chemistry where they said, oh, it goes right here, obviously. How the hell is that obvious? I never got it. But when I started applying mathematics to this and you can see the answers, it's way better. So that's what we're going to do. Okay, so we got to go back to the secular equation. Or secular determinant, excuse me. Okay, let's return to the secular equation. Look back in your notes to check out what the secular equation, a generic one, looked like. For our system, how big of a determinant are we going to have? So how many p-orbitals are we going to have in here? How many carbons do we got? 3. So what's our determinant size going to be? It's going to be a 3 by 3. So we got H11 minus what? Yep, ES11. Then we got H21 minus ES21, H31 minus ES31. And then we just keep moving the index over a little bit. Oh. This is therapeutic. It just feels like you're doing the same thing over and over again because it kind of are. I like it. It makes me feel good. S is the overlap integral. What that tells you is how much do the basis functions overlap? Not really complicated name. Well, it is complicated because you have to understand what a basis function is, all that stuff. But it tells you the quality of overlap. Now, what's all of this equal to? 0. Yep. This is just a secular equation. Okay? This is what we're doing to try and minimize the energy. And this is what my computers do all day, is try and solve these things. This is impossible to solve. Well, excuse me. It is incredibly tedious to solve this. I sent out that Wikipedia thing about the differential analyzer. I don't know if people read much about it, but that was like one of the first computers. It's weird. Okay. This is too hard to solve, at least in the time frame for what we have. People used to actually just be human calculators and calculate stuff, which is crazy to think about. Oh yeah, Hidden Figures or whatever. I never saw it. But my grandmother was a calculator. That's pretty funny. Yep. The nerd doesn't fall far from the tree. Let's apply. Hückel theory. Okay, so Sij, that's where it's a delta function. And then Hii was what? What did we say as a shorthand? Yep, alpha. And Hij is equal to beta. Okay. Now, we can label our carbons. That's carbon number 1, carbon number 2, carbon number 3. Some terms are going to just drop to be 0 because they're not near each other. Carbon number 1, what's it connected to, or is it adjacent to? 2. So any spots where we have 1 and 2, there will be a term at these 2 spots, right? Because they're connected. What about 1 and 3? Nope, that's just going to go away. This is going to be a 0. And what about this guy? Also a 0. Okay, 2 is connected to which ones? Both of them. So there should be a term for each one of these. And then in the last, those are true too. Okay, now let's apply our shorthand. See what we get. Okay, H11, what does that become? Yep, alpha minus E S11. S11 is 1 times 1. So this is it for that term, right? Okay. Next term to the right, we got H12. What does that become? Beta. That's it, right? Because it's 0, it goes away. And then the last term on the right, 0. So, because it's a delta function, so S12, it's a 1, 2. What would the value of S be? Yep, so it would be a 0. So there is an E here, but it's multiplied by 0 and it just goes away. Okay, so that's the first row. Second row, what do we got? This one's going to be beta. What about the one in the middle? Alpha minus what? Yep. And rightmost term for 2, 3? Yep, beta. Now here we said 0, no overlap. This one, beta, yep. This guy, minus E. And what's that all equal to? What's the goal of this thing, or why are we doing this? What are we trying to find here? We're going to evaluate the determinant, but what do we want out of this determinant? We want E, because that gets us the lowest energy state. From that, we can determine our wave functions from that. That's the whole point of this one. Now, my question becomes, how many people remember how to evaluate a determinant? With show of hands. Would it be beneficial to go over how to do a determinant? Yes. Okay. I'm going to erase this. Is that okay? Okay, determinants. Let's say B, C, D, E, F, G, H, I. We have that as a determinant. There are a couple different ways to evaluate this thing. This is the methodology I pick. So what you do is you break this down into smaller determinants. So the first one we're going to do is we're going to split off A. Any spot where you have A, you ignore the row in the column. So then we would have A times what determinant if we are ignoring this one and this one? Nope, we ignore that entire row. Yep, we're going to use this part. So we get E, F, H, I. Then we change signs to a minus sign. Now we're focusing on B. We have to ignore all the rows and columns with B. Bless you. Yeah, that's tough. What's going to be in the 2 by 2 determinant for B? Yeah. So now we got D, F, G, I. We move back to a plus sign. Joe, I can't remember what color you can see. What's the next best one?
You can use either red or green.
Okay. Now we got C plus C determinant. We got a 2 by 2. What's going to be in C's determinant, Joe?
C.
Yep. D, E, G, H. All of that one. D, E, G, H. Okay. Now let's keep going. We got A times. We do that bit multiplied by each other minus that bit. So keep rambling off what's coming up next. Anybody? Yep. 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 And then we would evaluate that. This whole thing is equal to 0, and you just solve. Okay, good refresher or quick intro. All right, let's go back to our secular determinant. We got to evaluate this thing. Remember, what are we looking for here? Yep, we're trying to find E. So let's break this thing apart. We're looking at that one first. What determinant do we have to deal with for that one, for the blue? We got that 2 by 2, right? Okay, minus beta. What's in beta's determinant? These 4, we got beta, beta, 0, alpha minus E plus C. Oops, what's C? 0, perfect. Boop, don't have to worry about anything else there. Okay, let's evaluate this further. First term of this determinant is what? Yes. Minus. Yep. Minus beta. What about in that next one? Yep. Yep, that's all we got. Okay, let's multiply stuff through, combine like terms. We got alpha minus E cubed minus beta squared E. What else do we got? Yep. Okay. Simplify that further. What's this all equal to? Yep. Okay. What could we call x here? Yep. Let alpha minus e equal x. Therefore, you don't need to do that. If you want to keep going through it, you can keep solving it. So now this term becomes x squared minus 2 beta squared x. Yep, thank you. Nope, it's good. Catch me when I do dumb stuff. Okay, let's break this thing apart. Pull x out. Let's break that one apart further.
Or will you divide it out?
We'll get there in a minute, but I want to break this guy apart. So, what is this called? Foiling?
Oh God.
Or factoring? I can't remember what the name is. Foiling? Okay. Break. It's not foiling. What is it? It's reduction. Factoring. Yeah, there we go. Okay, factor that.
Wait, do we do foil or no?
No, you would do foil to go this way. If you wanted to go this way, you would foil, right? Okay. Yeah. So when you have two polynomials or two, binomials multiplied. All right. Anyways, break this thing apart. Yep. Okay. And that's all equal to what? 0. Okay. So now, we have all of these things equal to 0. What's the goal of what we're trying to do here? Yep. Yep, we're trying to, this will result in a minimized energy, which is exactly what we want. We have 3 terms in. How many energies should we get out? 3. Okay, so finding the different E values. We got x is equal to 0. What was x equal to again? Alpha minus E. So if I manipulate that around, yep. Okay, then we had x minus square root of 2 beta, which is equal to E minus alpha minus square root, alpha minus E equal to 0. What's E equal to for this guy? Yep. That's what I was looking for, which means the other one. Yep. Okay. So now we have 3 energies. These are the energies of our different molecular orbitals. Question is, which is the lowest in energy? Given alpha and beta are numerically negative, like they're negative values.
plus radical 2.
Yep. That's going to be the one that's lowest in energy. Okay. So now, next question is what do the orbitals actually look like? So all we really know right now is we have some energy. And how many molecular orbitals do we have? 3. Yeah. We did that. I don't like that. 1, 2, 3. And what are the energies associated with these? Mm-hmm. Yep. Next one. Yep. Yep. And then what about this guy? Yep. That's all we know. Okay. But we had those trial basis functions, and we said they were a linear combination of those guys, right? So what we could do is we could look at the coefficients each carbon contributes, and we'll get an idea of what those MOs look like. But we gotta find those coefficients. So we have 3 orbitals. Three energies. We're going to call them 1, 2, and 3 because we're not very creative. Where? If we look at 1, let's say, we're going to have some coefficient of that one times its basis function. What did we say the basis function was again here? What type of atomic orbital? Yep, a 2p. So we're going to have 2p of carbon number 1. That's the contribution to it, to that orbital. How many other terms do we need here? So this is for carbon number 1. How many carbons does our system have? 3. So how many more terms do I need? We're going to have coefficient number 2 times, what carbon's this? Yep. And finally, what's the last? This is a lowercase v. These are a symbol. I think it's v. No.
I know it is. No, it's movie side.
I don't know. I will have to look at it. What carbon number is this guy, though? 3. Yep.
No, it's not.
Yeah. I'll have to look it up. Okay. So now we want to know these coefficients because then we'll know the contribution of each p orbital to this energy. And we'll know what it looks like. Okay. We can do this process for each of the orbitals. We're only going to do it for one of them just because it's tedious. I feel confident that you could do it for each of these others. but we're going to look at carbon number 1 because it's the lowest in energy. So given is the lowest in energy. And what was the energy of this one? Yep. We can use the following to get each coefficient. And that comes from the secular equation. If 0 is equal to summation n I is equal to 1 a sub I h k I minus e s k I. And what we're going to do then is plug in various values for E. We have one specific value of E that we're interested in. And then we'll plug in different values of HKI and SKI. Okay. This is going to result in 3 different equations. Okay, so results in 3 different equations. The first equation, A1 times, okay, we're looking at A1, we're going to have H11. What symbol did we give H11? Alpha, yep. Alpha minus E, our energy is equivalent to that thing. Alpha plus square root 2 beta. And then we have SII, or S11. Since it's a delta function, what does the value of that become? 1. Yep. Now we have to do this for carbon number 2 and carbon number 3. Okay, next term, plus A2. We got H12 beta minus alpha plus square root of 2 beta times S0. So we didn't really have to write that point out if we didn't want to. Plus A3 square root, we got 3, 1, 0. Yeah. Minus our energy, alpha plus square root 2 beta times 0. So that whole term is just 0. And that whole thing is equal to 0. We can do the same thing. We're going to get 2 more equations where we focus on carbon number 2 and carbon number 3. Times, what's this one going to be multiplied by? 0, yep. Plus A2. What does that first bit become? Not beta, but alpha. 2 beta, and that's multiplied by what? 1, yep. Then we got A3, which is just going to mimic that first one. And then the last one. It's kind of a waste to write this out, but we know it's going to be 0 minus alpha plus square root 2 beta. What's this multiplied by? Yep, 0. I got A2. What's this term going to be here for A2? Yep, beta minus alpha plus square root of 2 times, what's that multiplied by? Yep. And then we got A3. What's it multiplied by? Yep, minus alpha plus square root of 2 beta times what? Yep. Is all equal to 0. Okay. 3 equations, how many unknowns? 3. Hey! Because we don't know alpha, or we don't know A1, A2, and A3, but now we have 3 equations, 3 unknowns. We can solve for these things and get our coefficients. Hell yeah. What's that? Oh yeah, there's a lot of algebra here. Let's focus, so let's find expressions for A1, A2, and A3. That will get us coefficients of each of them, and then we'll have an idea of what those orbitals look like. Okay, so first equation, we end up getting A1 times alpha minus square root of 2 beta in brackets plus A2 times beta plus 0. Okay, let's combine some stuff. Can you simplify this further? Plus beta times equal to 0. Let's move this guy over so we get beta times A2 is equal to positive square root 2 beta times A1. What's A2 equal to? Yeah. Perfect. We're going to find another expression for the other one next time. Okay? And what this will do, it'll let us know the coefficients that these guys contribute to the lowest energy one. Okay? And then we'll draw them out and we'll see what it actually looks like. Okay?